Hello, my name is Mehrzad, and I'm presenting my PhD thesis titled Dynamic Management of Multiple Processor Resources to Improve Energy Efficiency Under Quality of Service Constraints. This is a popular science presentation, which is a simplified version of my thesis that is understandable by the general public. Start with the main research problem. We know that the computation demand is increasingly dramatically everywhere. For example, think about application domains such as online workplaces, autonomous vehicles, digital currencies, or virtual reality. Any of these domains require a significant increase in the computation and both the number of computers and the computation tasks that they are running. And these computers range from high-end data centers and cloud services all the way down to smaller processors that you can find inside your typical consumer electronic devices, such as your smartphone or your laptop or your drone. All these devices may contain one or several computer processors that are running a range of different computation tasks. So let's imagine what will happen if the energy consumption of these computers do not reduce and we keep increase the number of computers and the amount of computations that we're running on top of them. We're already facing serious problem with the energy expenditure at the global scale. We have the problems with global warming, the cost of electricity. Right now, we are in the middle of an energy crisis in Europe, and not to mention the operational time of battery-powered devices, which is directly dependent on the energy efficiency of these computers and the processors inside them. So this brings us to the main research question. How can we reduce the energy consumption of these processors without sacrificing their performance? Let's focus a little bit on this last term. What do we mean by performance? How much processing speed is really needed for a particular computer to provide sufficient performance? Let's look at this term, quality of service. We know that additional processing speed does not always produce more value. Quality of service is a term here that is used to help understand this concept. It basically means how much processing speed is required to provide sufficient value to the user. Think about a typical multimedia application, such as a video or a game that you're running on your phone. Let's say you have a particular setting. You can set the processing speed into 30 frames per second, or 60 frames per second, or 120 frames per second. For each one of these performance targets, you will get a different experience of the quality of the video. But beyond a certain point, if you raise the processing speed, you will not get a noticeable increase in the performance or in the experience that you're having with the game. For example, if you go from 100 frames per second to 500 frames per second, you will not get 5 times better quality. It's probably impossible to distinguish between these two levels of quality. So we want to move away from the typical approach in computer processor resource management approaches that will try to reconfigure the computer to achieve the maximum speed. And that also means you're consuming the maximum energy. And that wasn't a problem in the past because, first of all, we didn't have that many battery-powered devices, and second of all, we didn't care so much about the cost of electricity. But this is no longer the case. Now we want to transition into a new model where we have quality of service targets that will determine, instead of maximum speed, we want to have just enough speed as a target and try to minimize energy consumption without missing that target. Let's have a look at a baseline system. A typical computer today is organized in a multi-core architecture, which basically consists of several processing cores and usually a shared cache memory. each one of these cores contain a private cache memory or multiple private cache memories in a hierarchy inside the core. But then the larger cache space is usually shared among all the cores. And the purpose of these cache space is basically to hold the recently used data, because the idea is that if you're currently using some data, it's very likely that you will need that data again very soon. So you want to keep it close to the core so that you can access the data fairly quickly. But this cache space is usually limited, and if you want to have a larger memory, you need to go to the main memory, which is the DRAM in your computer. But the problem is that the DRAM is far away and it takes a long time to access that main memory. So it's very important that you use this available cache space in the processor very efficiently. One of the typical approaches that is used to control, to adjust the processing speed and energy consumption of cores is to adjust the voltage frequency of the core. We usually have something called dynamic voltage frequency scaling, and this way you can select between several levels of frequencies for each one of the cores, which also comes with a corresponding voltage level. So you can increase the processing speed by going to a higher frequency, but that also means you need to raise the voltage level, which will cause additional energy expenditure. And this can happen independently for different cores. Another resource control knob that we can have in the system is partitioning of the shared cache space. It means that you will determine how much and which parts of the shared cache each one of the cores can access. The advantage of having a partitioning in place is that you will avoid destructive interference between the data that each one of the cores is bringing to the cache. And on top of that, you can dynamically modify and change and control the sharing of the cache space between the cores, which will provide you with another tool to optimize the cache space during runtime. Let's assume that two applications are running in the system, and with cache partitioning in place, they are each one of them is occupying a certain part of the shared cache space. Let's say in the baseline system, it's an equal distribution, so each application will get half of the overall cache space. Now in this system, our goal is basically to dynamically adjust the different resources in the processor by controlling these knobs, which is the voltage frequency levels on each core and also the partitioning of the cache space. The goal of this modification is to find out an alternative resource configurations that will end up with a lower energy consumption, but without lowering the processing speed for any of these applications. So that's our goal. The proposed approach at the high level is to have a coordinated resource manager that has control over all these resources, basically different types of resources for different applications of the system. And we can show that this can lead to significant energy savings. Implementation of such system is not so easy. It comes with several challenges because you will have to have some ways to predict the performance and energy of different applications as a function of different resource configurations during runtime, which is a very difficult task. And on top of that, you need to be able to explore a large multi-dimensional configuration space. Think about all the possible combinations of cache allocations to a system that consists of many processor cores and all the possible combinations of voltage frequency levels. So this becomes a complicated design space that you need to explore and find the optimum setting. And all of this needs to happen with negligible overhead. So in this work, we have managed to propose several techniques, several resource managers that will perform just that, and it will We show with experimental results that such coordination between multiple resources across multiple applications, if it's implemented in an effective way, it can save a significant amount of energy without causing any performance degradation for any of these applications. Thank you very much.